This is the first video for the 6-4 fundamental theorem part. You may only watch this if you were absent or if you just wanted to go over the warm-ups or some of the information in there. So the warm-ups do say that the calculator is acceptable if you demonstrate your calculus first. In other words, write out your integrals and write out those things and kind of go with the idea of what the question's asking to find the multiple different representations so that if you did it without a calculator, you'd be able to do that. So in the first one, they want you to find total area of a region. And anytime they say that, our new concern is we have to find out where that region is above the x-axis and where it's below the x-axis. So we'd like to do the integral from 0 to 3 of the absolute value of that function then, so that we would get the area regardless of it being above or below the x-axis. So one way to do that, again, if it were calculator allowed, would be to go ahead and calculate the integral so that each time it takes a height, that height comes from the 2 minus x, and it takes its absolute value so that each rectangle's worth of area, or whatever it's calculating, is done above the x-axis. And if you're allowed to use a calculator, awesome. If you aren't, we have to be able to do that as well. So if you actually went and calculated this with your calculator, we should get 2.5. So pause the video and make sure you have all the entry skills in order to do that. Then when you come back, we want to look and say, well, if I didn't have a calculator, how would I have to do that so that I could still calculate that integral? So what we'd want to do is find the zeros, find what this graph looks like, and if it was a more complicated one, we'd probably start by finding the zeros. You and I have a pretty good idea of what this graph looks like because we're pretty good at graphing linears. I happen to know its y-intercept to be at 2, and that with its slope at -1, it should cross the x-axis right here at 2. So as far as doing the integral from 0 to 3, when I do that, I'm realizing I'm going to have to go one more unit past in order to calculate the area. So as far as integrals go, I could then do the integral from 0 to 2 of the actual curve, 2 minus x. Just thinking ideas of how I could carry this out. And add to that, now I'd want to take the integral, and again, so that this area gets represented as positive because they asked us not for the integral, they actually asked us for total area. So then I'd need the opposite of the integral. Actually, the way that's written, you can do it that way. Let me back up though. Most of the time it's written this way. The integral from 2 to 3, where that goes below the x-axis, of the opposite of the function 2 minus x. And you could bring that negative out in front, because we realize that what we need that to do is count as positive area in the actual total. So go to your calculator, make sure that both ways you calculate this, you end up with 2.5 so that you have those skills in their practice so that doesn't slow you down. The next part wanted to know if the area is the same as the definite integral from 0 to 3. The answer to that's no. So the actual integral from 0 to 3 of our function 2 minus x would only be 1.5 because it would be counting all the area in this region as positive, and all this area would count against that total, and therefore that net area would only be 1.5. So that represents the area as positive above the x-axis, but it also then subtracts the area below the x-axis, so it has that net sum. So is that the same as the area? No. Okay. Then we're going to actually start talking about the fundamental theorem again, because fundamental theorem, the part that we've already done, part 2, which is where we're going to start from today. Part 2 we said is called the integration or evaluation theorem. It tells us how to evaluate that. So hopefully you've worked on this graph a little bit, same idea. In order to do that, we need to take it apart, and we provided the graph so that you can actually see its zeros. This is a nice function where we can tell that it's got zeros at 3 and it's got zeros at -3. So if we're integrating from -5 all the way until +4, we're going to get some area above the curve and the x-axis, and we're going to get some area that's below. So when we go to do the actual integral, we'd want to take a look and see what they're asking us. They are asking us the total distance traveled, the total area here, because they're asking us in absolute values. So without a calculator, we want to think about how we can do this, and then you can set it up and actually use your calculator to check. So we want that area to count as positive. We'd want this area in here definitely to count as positive. But they're also saying that they want this area below the curve to count as positive as well. So to do that, we'd have to be able to flip that part of the curve up above the x-axis so that its area would count positive in our sum. So those are the three areas we would need to add together. The good news is we definitely know where those bounds are that we need to switch. So from -5 until -3, the function is above the x-axis. So I can go ahead and use the actual function above the x-axis for that part. So this is how do we calculate that absolute value if we aren't letting our calculator do that for us. So really going through and coming up with ways. The next part of that curve from -3 to +3, however, we want it to count the opposite in there. So -3 to +3, we want it to take and flip that entire function up above the x-axis. So that would be the opposite of x squared minus 9, so it'd be -x squared plus 9. Practice good notation because that's the basis of all your rectangles. And then from +3 until +4, we're back to being okay with it using the function's actual values. So at this point, if it was non-calc, then you'd go do your antiderivative for each part and evaluate that. But why don't you go ahead, pause the video, evaluate both ways using a calculator for the way we wrote it out, and then you also finding the right keystrokes so that you can check that and make sure that both ways that you calculate that, you come up with an integral value of 54. And finally, last thing, we've got one more going along with this area theme and how we calculate. One more where they're going to ask us to find area of a shaded region. And the shaded region may or may not look that shaded on yours. The shaded region is between those curves and the x-axis, that amount of area that's trapped in there. So our plan would be that, well, normally it would just be the area under the curve, but unfortunately this area is kind of caught between two curves. So a plan might be to first of all figure out where these two curves intersect. And to do that, we would come up with their intersections, where -3x plus 4 equaled x squared. We could bring that over, do all the factoring and all those kinds of things that we want, and we end up with, so again, if you had to do this non-calc, okay, and then you'd be looking at seeing how you could get your factors in here. We'd be looking at this. So solutions-wise, they're going to intersect when x is -4. Not a concern here because it's not in our the part that we're actually looking at. So we know that this is 1 comma where they intersect, and we can see it in the graph. But again, you'd have to have some way of verifying that so that you wouldn't be going off what it looks like. And then when I plug 1 into either function, I get 1 out. So I'm at 1, 1. The thing I really need to know though is where this interval is ending. So as I'm looking at this and I see that my interval is ending at a point that I can't read, I've got to have a plan to calculate that. So that is where -3x plus 4 has a 0, where that -3x plus 4 is outputting a 0. We'll go ahead and solve that. We find out that that's at 4/3 so that we know where our upper bound for our integration is. This curve starts at 0, 0. If you plug 0 into x squared, you get 0, and it ends there. But it's trapped by the orange curve on the first part till 1, and then from 1 to 4/3 it's trapped by the blue. So we really need to think about this as two separate integrals. We're going to integrate from 0 to 1 the x squared function, and then we're going to integrate from 1 until 4/3 that -3x plus 4 function. So again, it would be wise to pause the video, either do area, which you could definitely do for the linear one, and or antiderivatives, and work out a calculation so that by the time you're done with some work, that you can show that the area between those two, or the value of that definite integral, is half. There's a second video to this, so make sure that if that's what you need to be watching, you do that.